So thermodynamics is what we call the study of energy and its interconversion. The first law of thermodynamics is the law of conservation of energy. And another way to state that is the total amount of energy in the universe is constant. You can never design a system that will continue to produce energy without some source of energy. A long time ago, people thought they were coming up with these perpetual motion machines. You know, you get it started and it would keep moving all by itself. And it's like, maybe we could harness this and, use it to generate energy. Well, the energy content of the universe is constant. All we can do is transform energy from one form to another. We cannot create energy. So conservation of energy means that the sum of the energy changes in the system and the surroundings must be zero. So the energy change remains. Remember, delta means change. It's the final minus the initial. The change in energy of the universe is equal to zero, which means that the change in energy of your system plus the change in energy of the surroundings must add up to zero. And that's something we're going to use in lab today. Whatever one loses, the other gains. The internal energy of a system is designated E. And that is the sum of the kinetic and potential energies of all the particles that compose that system, whatever that system is. The change in that internal energy depends only on the amount of energy in the system at the beginning and the end. It doesn't depend on how the change happened. And so we say that the change in energy is a state function. It has to do with the beginning state and the ending state. A state function. It's a mathematical function whose result only depends on the initial and final conditions or states, not on the process used. So we can say that the change in the internal energy of a system is equal to its final energy minus its initial energy. If we're talking about the reaction, a chemical reaction being the system, then we say the change in internal energy of the chemical reaction is equal to the energy of the products, the final state, minus the energy of the reactants, which is the initial state. So we need to understand what a state function is. So here's a picture of a mountain. And there are two ways to get to the top of the mountain. You can go up, let's do path A first. You can hike up path A, which is 12 miles of distance traveled because you're walking back and forth. Or you can go up path B, which goes straight up the mountain, and that's 5 miles, but it's straight up, right? So personal preference, which way you want to go. If you're starting down here at sea level at 0 feet, and you both end up here, and one of you took path A, and one of you took path B, what is the change in elevation that you experience? Does it depend on how you got there? No. Change in elevation is a state function. It's where you are now minus where you came from. So up here, looks like about 10,000 feet. Your change in elevation is 10,000 feet. Doesn't matter how you got there. And that's the way the change in internal energy is. It doesn't matter how it happened. Is distance traveled a state function? So if we're starting here and ending up there, if I take path B, it's 5 miles. If I take path A, it's 12 miles. Does it matter how I got there? For the amount of walking I did, the distance traveled, does that depend on what route you took? Yes. It does. See, I can get to Reedley by driving down 41 to 99 to Manning. Or I could get to Reedley by going north on 99 and going up over the Arctic Circle and coming down around through Antarctica and come up from the south. I'd end up in the same place. But the distance traveled would be hugely different. That's not a state function because it matters how I got there. With energy changes, it doesn't matter how you got there. We use energy diagrams to help us visualize the flow of energy. So here's a reaction, carbon dioxide decomposing to carbon and oxygen. And in a graph like this, we're looking at internal energy increasing as we go up. So here's our reactant at the bottom and our products at the top. And this tells us delta E is the final minus the initial. The products are the final, so here's their internal energy. There's no numbers here, but it's this point here. The final energy minus the initial. That's a positive number. Okay? The change in internal energy is positive. It's greater than 0, going from the reactants to the products. This is a positive number because energy came in from the surroundings. How could the carbon and the oxygen have higher energy than the CO2? They must have gotten energy from something else. They got it from the surroundings. Energy came in. So there again, energy is like money. When money comes into my bank account, I feel positive about it, right? Energy coming into the system is a positive thing. And we call that an endothermic process because the energy is coming in. So the energy of the system increased. It had to come from somewhere. It can only come from the surroundings. The change in energy for the surroundings then is going to be negative. It lost energy. Here's a different diagram. We're looking at this same reaction, but in the other direction. Carbon reacting with oxygen to form carbon dioxide. Now the reactants have a higher internal energy, and the product has a lower internal energy. The change in internal energy is the final minus the initial. The initial was higher. You take a large number and subtract it from a small number, and you get a negative number, right? So the change in energy is less than 0, it's negative. That means energy left the system. Where did it go? Into the surroundings. Okay? When energy flows out of the system, it has to all go into the surroundings. Energy flowing out of the system, the change in energy for the system is negative. If that's negative, energy is flowing into the surroundings, and that's positive. And so we can say that the change in energy of the surroundings is equal to, but opposite in sign, from the change in energy of the system. Because if I give Jose $5, that's minus $5 for me and plus $5 for him. Same number of dollars, but the sign tells us which direction it went. So it's like money in your checking account. Any questions? Well, how is energy exchanged through the system and the surroundings? 2 ways, heat and work. Heat is Q. Don't ask me why. And W is work. That makes more sense, doesn't it? W for work. These are not state functions. The amount of heat transferred, the amount of work done does depend on the process. But when you put them together, they give you the change in energy, which is a state function. So for Q, it's positive if the system is gaining thermal energy. It's negative if the system loses. Work is positive if work is done on the system. Think of perhaps a massage, okay? When someone does work on you, when they do a massage to you, how do you feel about that? Is that nice? Yeah, right? That's a positive experience. When you do a massage to someone else, when you are working on them, then that's a negative. You're giving out. So work being done on you, or you could think of for you, is positive for you. You doing work for someone else is negative. It's important that we get the signs straight. So the change in internal energy is equal to the heat plus the work. So here we have a smooth pool table. We have a ball with an initial kinetic energy of 5 joules. As the ball rolls across the table, it slowly loses velocity, doesn't it? It will not keep going forever. That's because of friction between the ball and the table. And so as the ball goes across this smooth pool table, it's losing 0.5 joules of energy. And then it collides with another pool ball. When you have a pool ball that's sitting still and you hit a moving ball into it, what happens? Usually the ball that was still, the purple ball, gets the energy and moves, and this ball basically stops. It's kind of a weird thing. It's because this is an elastic collision. Most of the energy gets transferred as kinetic energy, and it doesn't get lost as heat. So the energy from this white ball is transferred to the purple ball. It had, by the time it got over here, it had 4.5 joules left, and so it transfers that to the purple ball. After the collision, the white ball has 0 joules. It has no energy. So the work that it did was minus 4.5. That was energy that left the ball. It did the work on the purple ball. Q was a heat energy transfer through friction with the pool table. That's minus 0.5. And overall, the change in internal energy for this ball is 5.0 joules. Because right now, it has no energy. Initially, it had 5. So 0 is its final energy. 5 was its initial. 0 minus 5 is negative 5. Does that make sense?
How do we know it lost point?
That's not something you can really measure. This is kind of a, let's say this happened. Yeah. Yeah, measuring something like that is challenging. Any other questions? Here's a rough pool table. This is maybe a pool table that's kind of been abused. And the felt's not nice and smooth like it's supposed to be. Here again, we have the cue ball starting out with 5 joules of energy. But because the surface is so rough, it loses 3 joules of energy. It's slowing way down as it goes over here. By the time it collides with this purple ball, it only has 2 joules of energy left. It's going to transfer those as kinetic energy to the purple ball. And so it still has 0 energy at the end. The change in energy for it is the same, but W and Q are different. They add up to the same, but each of them is different. Now the work was minus 2 joules, and the heat lost was minus 3 joules. Any questions? Change in energy is a state function, doesn't depend on the process. Work and energy do depend on the process. Yeah, I just said all that. You can read that later. So heat is the transfer of thermal energy. This occurs when the system and surroundings have a difference in temperature. If you put an ice cube in a cup of hot coffee, what happens? The ice cube melts, so it warms up, and the coffee cools down, right? And that's why you would put an ice cube in a cup of hot coffee. Have you ever seen a glass of water just spontaneously develop an ice cube? That's just crazy to think about, isn't it? It doesn't happen. Heat energy flows from high temperature to low temperature. There has to be a temperature difference in order for that to happen. Temperature is a measure of the thermal energy. So temperature is how we measure the thermal energy. And heat's going to flow from the matter with the high temperature to the low temperature until they reach the same temperature. And we call that thermal equilibrium. At thermal equilibrium, both objects are the same temperature and there's no more transfer of heat.